All right, so Newton's law of cooling, that's pretty cool for an application. How about we look at something a little bit more vigorous? Let's assume that we had a zombie apocalypse. And we wanted to model this, of course. So how would we do this? Well, we would use a model where the rate of change of the infected population is directly proportional to the product of the infected population and the uninfected population. So the reason that we do this is because once people are infected, they can't get reinfected. Okay, so there's sort of a product term in there that takes that into account. So if we write an equation for this, let's define some invariables here. Let's let z of t be the infected population. So those are the zombified individuals. And let's let u of t be the uninfected. So zombies and uninfected. And those are both at time t. So then this equation, our total population is going to be p. That's a constant. So this differential equation says that dz dt, the rate of change of the infected population, is directly proportional to, so it's a constant multiple of the product of the infected, that's z, and the uninfected u. Okay, so this is actually a very common model for the spread of infection. So this could be, spread of a zombie apocalypse, could be spread of a rumor, could be spread of coronavirus. This is very simplified model. There's a lot more that's going on, but we're trying to understand on the very basic level what's going on here. So, well, this is a separable differential equation. We can solve this. What we'll do is we'll write the uninfected population in terms of z so that we have one variable. So u is actually the total population minus the infected z. Okay, so this is your uninfected there. So now we've got one variable. So now let's multiply both sides by dt. So this will come up on the right. Divide both sides by z and p minus z on the left-hand side. So we get dz over z p minus z, and then k dt on the right. And so we've got things separated. What next? That's right, integrate both sides. So integral of dz over z p minus z is integral k dt. Well, we know what to do with this integral on the right-hand side. What about this one on the left? What method of integration are we going to use there? Well, it's a polynomial in the denominator, and basically it's 1 on top. So it's polynomial divided by polynomial. That's partial fractions. So we can do partial fractions on this. Our partial fraction decomposition is going to look like a over z plus b over p minus z. Okay, and if we do that partial fractions, we will get 1 over p and 1 over p as our two constants, a and b. So I'll leave you to check the details on that. So on our left-hand side, we've got integral 1 over p divided by z plus integral 1 over p divided by p minus z. And then on the right-hand side, k times dt. Well, 1 over p is just a constant, so we could pull that out in front. And the plus here we're going to write as a double negative. And the reason that we're going to do that is because the derivative of the bottom here is -1. So I want to have a negative on the top. So see, if we go back here, this was a plus. So let's change that plus to double negative. So now on the right-hand side, we've got the easy integral, and we've got 2 logs on the left-hand side after we factor out that common factor. Let's go ahead and do that. So take our 1 over p here out in front, right there. So we got 1 over z dz left, and then minus the integral here of -1 over p minus z. So -1 over p minus z. So now this side looks like g prime over g. So we've got our 1 over p out in front, and then the integral of 1 over z dz is log of z, and I don't need absolute values because z is positive. And then we got g prime over g, so it's going to be natural log p minus z. And again, p minus z has to be positive. The population's bigger than the infected portion of the population. On the right-hand side, we integrate and get k times t plus our constant of integration. So remember that subtraction outside the log is what inside? Division. So we can simplify this as 1 over p natural log z over p minus z is kt plus c. And now we can multiply both sides by p. So multiply by p on the left and multiply by p on the right. This guy's got to come in times each piece. So on the left-hand side, these guys cancel. We just get natural log z over p minus z. On the right-hand side, p times kt, kpt. And then c is our arbitrary constant times a constant p still gives an arbitrary constant. So that arbitrary constant absorbs the scalar multiplication. So now how do we solve for z here? Well, we got to undo that log. And we do what? E. That's right. So we got to exponentiate on both sides. So if we exponentiate on the left, exponentiate on the right. So e and ln here will cancel out. I get z over p minus z. On the right-hand side, I've got that exponential e to the kpt plus c. So again, we're going to break this apart. You add the exponents that comes from a multiplication. So that's the same as saying e to the c times e to the kpt on the right-hand side. And this e to the c, that's a positive arbitrary constant. So this is greater than 0, and it's arbitrary. So let's rename that, and let's just call it c. So we've got z over p minus z is c e to the kpt, and there is a restriction here that c has got to be greater than 0. So what next? How are we going to solve for z here? Well, we somehow got to get our z terms together. Let's multiply both sides by p minus z. If we do that and then collect our z terms on the left-hand side and then factor out a common factor and divide. So we got some algebra to do. It's not hard algebra. It's a little bit messy, but we got some algebra to do. So if we do that algebra, we can show that the constant out in front, that positive constant, is actually z0 over p minus z0. So z0 is the amount infected at time 0. So, maybe it starts with 1 zombie, then z0 would be 1. And we can, with that constant, we can show then that z, our function for the infected population, is p times z0 e to the kpt over p minus z0 plus z0 e to the kpt. So notice here, if you look at this proportion of the population that is infected and you take a limit of it, so if you take the limit of z of t as t goes to infinity, so what happens in the long term? Then we're taking the limit of p z0 e to the kpt over p minus z0 plus z0 e to the kpt. So t's going to infinity here. So we've got a number in the denominator here, and then plus an exponential term, and then another exponential term on the top. Well, both this piece here is going to infinity, and this piece is going to infinity. So this thing looks like infinity over infinity. So you could look at just the dominant terms there, or you could use L'Hopital's rule. Let's just consider the dominant terms here. So this will then equal the limit of p z0 e to the kpt over z0 e to the kpt. And then look, these guys cancel, and these guys cancel, and we're just left with p. So what does that mean? That means that if we graph this, our graph is going to start out at z0. So this is z0 right here. And then P is the entire population. And what's going to go on there is it's going to start out increasing exponentially, but then as more people get infected, there's less uninfected people, so the rate of growth slows down, and then it asymptotically approaches the confined population. So like we had, coronavirus on campus and it was contained and they quarantined us. This is what would happen with the number of affected people over time. Eventually, everybody would be infected, and then there would be no more spread, and then they could drop the quarantine. So of course, unfortunately, that would mean, it could be that 2 to 3% of people died. That's not a good situation if you can avoid it. But in terms of zombies, what does this mean? Well, this means that eventually everybody's a zombie. So notice that in our original equation we had dz dt is k times z p minus z, that's just the logistic equation in disguise. So dz dt equals kz p minus z if we do a little bit of rearranging here. It's k times p z, p minus z over p. So I just multiplied and divided by p. And then that means that dz dt is k times z, and then this is p over p minus z over p. So this is z and 1 minus z over p. And then I rename this constant k times b to be my new constant k. So that's really just the logistic equation. And the logistic equation gets applied in lots of practical situations. So logistically, that can model things like tumor growth, chemical reactions, changes in language, rumor spreading, neural networks, and a lot more.